In today's video, we'll learn about Kepler's three laws. Kepler's three laws helped us redefine how we imagined our universe. Before Kepler's discoveries, Earth was regarded as the center of the universe, and planets revolved in circular paths. Kepler's first law states that all planets move in elliptical orbits with the Sun at one of the focal points. And if a line is drawn from the Sun to any planet, the area sweeps out underneath equal area in an equal time interval, no matter the location of the path of the planet's orbit around the Sun. And Kepler's last law states that the square of the orbital period of any planet is proportional to the cube of the average distance from the planet to the Sun. So we see if we take the period squared is equal to 4 times pi squared divided by capital G times the mass of the Sun, all multiplied by the radius cubed. And we define t as the period, and our 4 pi squared divided by capital G times the mass of the Sun can be symbolized as k subscript s as a constant with a value of 2.97 times 10 to the negative 19th. And with this law, we are able to find the mass of a planet orbiting the Sun by rearranging our equation for the orbital period of a planet. In our first example, we see that if a satellite moves in a circular orbit around Earth, and it takes the satellite 110 minutes to complete one orbit around Earth, determine the altitude of the satellite if Earth's radius is 6.38 times 10 to the 6th meter. So in part A, we're asked to solve for the altitude of the satellite. And we know our radius of our orbit is equal to the radius of Earth plus our height above Earth, or our altitude. So we can rearrange this equation to get our altitude by itself. When we do so, we see that the radius of the orbit minus the radius of the Earth will give us our satellite's altitude. So the radius of Earth was given to us. However, the radius of our orbit is unknown. If we apply our equation for a period, we see that our period squared is equal to 4 pi squared divided by capital G times the mass of Earth times our radius cubed. Our radius cubed will be our radius of our orbit. And if we rearrange the equation to solve for r, we'll get a new equation where r is equal to our period squared times capital G times the mass of Earth divided by 4 pi squared, all taken to the 1/3 power. And so we know our period, G is a constant, as well as the mass of Earth. So we can plug in the information we're given to solve for our radius. However, our period is given to us in minutes, and we must first convert our period into seconds. So it takes 110 minutes to complete one orbit around Earth. And we see that for 1 minute, there are 60 seconds. You see that our minutes will cancel, and our period in seconds will be equal to 6.6 times 10 to the 3rd seconds. And now we can plug in our values for the following equation. Our period is 6.6 times 10 to the 3rd squared times the constant of G, which is 6.67, times 10 to the negative 11th, times the mass of Earth, which is 5.98 times 10 to the 24th kilograms, divided by 4 pi squared, all taken to the 1/3 power. And when we do so, we'll see that our orbit radius will be equal to 7.61 times 10 to the 6 meters. Now that we know the radius of our orbit and the radius of Earth, we can solve for our satellite's altitude. So, satellite's altitude is equal to the radius of the satellite's orbit minus the radius of Earth, which is 6.38 times 10 to the 6th power, will give us an altitude of our satellite above Earth's atmosphere of 1.23 times 10 to the 6 meters. And in part B, we're asked to find the acceleration due to gravity, the satellite's given altitude. In part B, we're trying to solve for the acceleration due to gravity. We know that the force due to gravity is equal to capital G times the mass of Earth times the mass of the satellite divided by the radius of our orbit squared is equal to force times gravity, or it can be rewritten as the mass of the satellite times acceleration due to gravity. Since we're trying to solve for the acceleration due to gravity, we can divide each side by the mass of the satellite, which will give us the final equation of capital G times the mass of Earth is equal to the orbital radius squared. We can plug in the values for G, which is 6.67 times 10 to the negative 11th times the mass of Earth of 5.98 times 10 to the 24th kilograms divided by the orbital radius of 7.61 times 10 to the 6 squared. And when we calculate this out, we'll get a new value for the acceleration due to gravity of 6.89 meters per second squared. In our second example, a moon of orbit called Io has an orbital period of 1.77 days and an orbital radius of 4.22 times 10 to the 5th kilometer. From the data, determine the mass of Jupiter. If we summarize the information we're given, see that our period is equal to 177 days, and our radius of the moon's orbit around Jupiter is equal to 4.22 times 10 to the 5th kilometers. Since our period is in days, and we know our period will have to be in seconds, we can convert our period of 1.77 days into seconds. So for one day, there are 24 hours. So our days will cancel out, and for every hour, there are 60 minutes. You see that our hours will cancel out, and for every minute, there are 60 seconds. And so our minutes will cancel out, and we'll be left with seconds. So Jupiter's moon's period is 1.77 days, or 1.53 times 10 to the 5th seconds. Our equation of a period gives us that our period squared is equal to 4 pi squared divided by g times the mass of Jupiter, all times the radius cubed. And since we're trying to solve for the mass of Jupiter, we can get the mass of Jupiter by itself, and we'll get our new equation that is equal to 4 pi squared times our radius cubed divided by capital G constant times our period squared. We can plug in the values that were given of Jupiter's moon to Jupiter is 4.22 times 10 to the 5th kilometers cubed divided by our g constant of 6.67 times 10 to the negative 11th times our period of 1.53 times 10 to the 5th seconds squared. And when we calculate our equation out, we see that the mass of Jupiter is equal to 1.90 times 10 to the 27th kilograms.